Okay, we went for a long time with a really intensive pace. Now the intensity of our studies will be a little bit delayed because the next week I'm not here. So I will try to prepare PowerPoints and communicate them, and maybe if it will be technically possible, I will make short lectures by Skype meeting. I will send an announcement to everyone who is in the group. So those who are in SDSU,
Yes.
probably will not notified because you anyway percepting everything remotely. So I will try to do next lectures in remote form. But
Sorry.
when I next week, I'm not in South Dakota.
Oh, okay.
Okay, that's
Dr. Killian, like,
but if you have chance, try to attend same place, same time, and you will get some information.
how we get help on our lab? We have problem in lab,
Uh,
you know.
please send emails to me and to other members of the class. We should
Okay.
try to help each other and be active and cooperative.
Okay, no
So,
problem.
so
Thank you.
the plan, the biggest event that we are going to have regarding this class is last Thursday of February, and anyone volunteering to contribute to this event will be highly rewarded regarding credits toward the course. So we are going to cover advanced preparation of Gaussian software, and after we do these presentations, we'll switch to another piece of software. So we should kind of review what we will be knowing by this date. So I'm going to leave a key while I'm not in the city, so anyone can go to this computer room and practice a little bit more. And we will have a meeting on Tuesday, February 26th, just a day before, 2 days before the presentation. So there I will come across all topics that I needed for Thursday. So even if you want to present and you are not comfortable doing those things, I will cover everything from scratch, so that for presenters on Thursday it should be an easy life. For scientific part of today's lecture, we will keep accumulating ideas of how to get total energy, and we are approaching the Hartree-Fock method, which is a big development of the whole human society. So we are not going to capture it at once. We are going to make small steps, and we are gathering all nearby important information or fundamentals. And then approximately by this date, or maybe even next lecture after those presentations, we will complete Hartree-Fock. And specifically today we will play a little bit more with, we will focus on crystal systems. Okay, so here is the same list I was showing last time. Those are possible options for presenting on February 8th. Let me go across this list, because it is really big amount of information, of practical information, which is really helpful, and I will not be able to compress everything and present everything in one lecture. It really needs your help, a cooperative effort of making some great event. So when we were meeting last Tuesday, we briefly covered, we spent 2 hours and covered these two subjects, and they are most critical for practical implementation. So the idea was that the Gaussian software can be executed with a moderator with Gauss view shell, Gauss view program in between, or it can be executed direct through the command line, including completely all procedures. So preparing structure, preparing the atomic model, giving all commands, all instructions to the software what needs to be computed, all input files, and analyzing all output files can be processed just by sitting by the command line and typing some word. So we did this, and the protocol of our meeting is on D2L. I'm going very briefly cover what we did in a little bit more details. And we also were discussing how to analyze the output of the Gaussian software. Without Gauss view. So we were looking where to look for total energy and where to look for Homo-Lumo gap. So it was briefly what we did on Tuesday. So this is covered. Another very attractive, very beautiful, maybe it is not the top importance for scientific research, but it is a pleasant part of computational research is to visualize molecular orbitals. And this is the minimal task that we will do on Tuesday before this date, and I hope that someone will select this topic, or maybe we will even split it between several people, because Gaussian and Gauss view help to prepare nice people. They are helpful in understanding science. These two methods that I have listed first, second, are less practical, but they are more important if you are thinking about writing introduction to your paper or to your thesis, or you want to be very rigorous and explaining to someone else what you are doing. So there are several available electronic structure methods, and one of you can decide to just list them and briefly tell how they relate to each other. This is not a secret. It is not a secret information. It is in textbooks. It is in Gaussian manual, and to those who select for this, I can provide some help. Another thing that one needs to specify while running Gaussian software is so-called basis sets. It is the subject that we were briefly covering last 2 lectures ago. Atomic orbitals, which serve as building blocks to find electronic structure of everything. And exact atomic orbitals, as they come from a hydrogen atom, are not best functions analytically. There are some functions that behave much better for processing in numerical form and in mathematical form. And those approximate representation of those hydrogen orbitals, set of those orbitals, are referred to as basis sets. There was and is big research which approximation to those orbitals should be used. And if you try to play with Gauss view or directly operate Gaussian, there is like 20 choices. And if someone volunteers to review them, it will be helpful for all of us. When we were gathering in the lab on Tuesday, we were selecting this HF, Hartree-Fock method, and for basis set we were using 102 easy set of orbitals. There are few other options, and it would be great if you can cover it with us. Well, there is another possibility to select when you are running the software. You can select that give a direction to the software that you need total energy, or maybe you want to optimize geometry, so we know this task. But there are some other tasks that you can assign. You can ask for normal modes, for infrared spectra, for UV visible spectrum. You can find some barriers, some transition state search, and it is also worth of mentioning. And there are two other things. When one when one tries to use different pieces of computational software, there is a group in this university, there is a group in other university, they can use same computational method implemented in different software. How do they talk to each other? So they can compare the numerical output in numbers, in data, or they can summarize their electronic structure in some standard form. One of the standard forms to summarize the electronic structure is so-called density of state, which can be built out of output of Gaussian. So it can be built in numerical form and it can be plotted. Those are other options to present. So please keep thinking about it, and we will discuss if anyone wants to, who wants to present what, when we meet 1 week and a half from now, on February 26th. Okay, so if you do not mind, I can briefly go across what we did in the lab. So we have, I'm not going into technical details, it is just a review. So we have inspected the input files for Gaussian, and we have noticed that the .com file consists of two parts. The first part is instructional, and second part is atomic model. And the instructional part includes the data about which method to use. So it is followed after the number sign. Then slash, which places other things are more service words. They are not so important. And these two numbers are also important as they specify whether the model that you are going to describe is neutral, whether it has zero charge or it can have some other charge. And the second number here, one, stands for multiplicity. So for most objects, one wants to describe singlets when number of electrons up and electrons down compensate each other, but sometimes one needs to look for more exotic configurations. Then there is a second segment that contains names of elements and coordinates. So if one prepares a file like that, one can directly submit it to Gaussian without Gauss-U program. When you look on the .log file, when you are looking on the output, you can scroll through this big file and find several important things. One can look for the CF done keyword and find what is the total energy. A few lines after that, there is a list of numbers which are abbreviated as OCC and EIRT, which stands for occupied orbitals, energies, and empty orbitals. 1, 2, 2, 5. And the list starting from here goes this serpentine way, with energy increasing, and energy is presented in atomic units. And if one needs the energy of highest occupied molecular orbital, one gets to the end of the list of last occupied eigenvalue. There, this one will be HOMO. If one needs the lowest unoccupied, one looks for the first in the list that is notified with this EIRT. This one will be LUMO. Okay, so we all now are more or less on the same page. And, this information, which is coming up in the text form from the command line, can also be seen with the Gauss view. If you are doing it for a couple of times in the life, if you are not going to make professional runs of 1,000 different molecules, you can do it once with Gauss view, which is very pleasant by mouse operating things. So if you click for results option, you open the .log file. Open .log Gauss view and look for result. There a window pop up that shows the total energy of the model. Maybe some other summarizing thing. You can draw energy and look for the distribution of charge, which atom, which ion in the model get more electrons, which one get less electrons. And what we are going to do, our program minimum for February 26th, is molecular orbital. Molecular orbital. So I will be talking about it in more details, even a little introduction, so that we feel comfortable and know what to expect. So when you do run Gaussian software, it generates at least two files. One file is log that contains some readable text information explaining the properties of the system, and another is .chk. This .log contains energies, and chk contains wave functions for molecular orbit. But they are hidden in the very non-human encoded form. There is a little effort to extract them from there and plot. So in order to process the PHP file, we need to convert into .fchk. I know this has nothing to do with science, but it is the language of the creators of the Gaussian software, and it is done by command line command. And then if this file is read into Gauss view, one can click on floating orbitals and select which molecular orbital you want, number of molecular orbital. Then check on presenting a surface. If we are going this way, it plots the surfaces of the same value of when this function equals to this constant. Here is an example how it may look like for the model that we were doing on Tuesday in the Arts and Science placement. And a week and a half later, we will do it in more details. You all will practice, and hopefully on Thursday someone will present more details so that it will be comprehensive. Sounds good? Okay. So I will take a slower pace, not trying to be not too detailed today. So also I'm trying to make a sort of announcement, simplified explanation what Hartree-Fock method. So in the previous lectures we were at the very beginning. We started modeling our molecules and materials in quantitative form based on molecular Hamiltonian, right? So we specify position of ions, and then we know that there are some electrons around. Then when we do build molecular Hamiltonian, we see that there is a term for electron-electron interaction. E, and it is plus 1 over position of electron I, electron J, and that's it, right? If we are in atomic system of units, then all charges and constants are ones. So if we bring together two electrons, they start to repel, and there is a noticeable amount of energy contributing to the total energy of system. So if you imagine some molecule and start building it as a tinker toy, as we have some positive ions, and then we throw in first electron. So no electrons, only ions, all positive. Throw in one electron. The ions will impose the attractive field, and the electron will find the best shape that it wants to take in this field. It will take a ground state. And if there are several ions, probably it will be delocalized over several ions. Electron sits around ions. Then we can throw in the second electron. This will be our wave function, ground function for first. When we throw in the second electron, it does experiences additional force, additional potential. It experiences the potential imposed by ions, which is attractive. And at the same time, it feels the repulsion of the first electron, which is already sitting there. Okay? So second electron repulsion. And therefore, the state, the orbital, the quantum state of the second electron, even it does tend to go to the ground state, will be different from the orbital where the first electron is. Probably it will try to find some places where first electron is not present. It will be some different function. And if you bring the third, fourth electron, each of them will experience more and more complicated force from all this assembly of ions and electrons. And therefore, each next orbital will take different shape. So those orbitals, those wave functions for separate or single electrons are independent. So we are addressing substantially multidimensional function of many variables. And finding it at once is very challenging. So the Hartree-Fock theory gives a recipe how to substantially simplify this problem. Multi-dimensional problem. Multi-dimensional problem. So it gives a way to reduce dimensionality in the calculational procedure. Calculational procedure. So the main idea of the Hartree-Fock method is that if we put in the system all electrons except the last one and compute the potential that is imposed only on the last electron, then this average potential created by all but one electrons can help us several orbitals. So we will be solving Schrödinger equation only for one, for last electron. And Schrödinger equation has several solutions, several orbitals. So the idea, the approximation is that those orbitals which are found only for the last electron can be used as an approximation for all orbitals. We are not looking for first and second and third independently. We are looking for the orbitals which are found only for the last electron, and then we carefully populating them with electronic occupation. And mathematically, it takes some effort. Therefore, we are going to spend a couple of lectures. Let me try to verbalize it. Potential affecting last electron serves to generate auxiliary orbit. Auxiliary orbit. And these auxiliary orbitals, according to Hartree and Fock, are enough to use them as building blocks for finding multi-electron wave function. So it is very non-trivial idea, but it makes calculation much simpler, and sometimes it gives reasonable results. These auxiliary orbitals are used as building blocks for multi-electron wave function. And they can be plugged into Slater determinant and then used to compute total energy, and observables. So by now, we do not know Hartree-Fock method yet, but we get a general idea. So it is a method to simplify multi-electron problem, to reduce dimension, and the essence of the method is to get very specific building blocks for finding multi-electron wave function. Okay, so we are done with this, and on the next lecture, next meeting, we will keep developing more precise, detailed determination of Hartree-Fock. Now, let's play a little bit more with spins, because those are simplest objects that keep the nature of multidimensionality, multidimensional quantum properties, and they help us to understand what we are getting in this Hartree-Fock theory and other theories. So if we understand what are challenges and how to avoid them, then we will be in much better shape for the remaining part of the course dealing with electronic structure. So last time we were discussing one spin, which can be up or can be down, and we agreed that we know how to formally detect in which state system is if originally it is in the superpositional state. We found that probability to stay in state whatever alpha is E alpha squared. But we get the procedure through Ra times projector times ket. So probably one can do the same thing for two spins. Then we need to number them to tell that this is particle number 1 and this is particle number 2. Right? And since they are independent, the number of basis states for this combined system of two spins will be bigger. Two by two equals 4. Okay. So in case we have first spin sigma 1 plus E alpha 1 alpha 1. I'm going to maybe write a little bit more than typically, but most important ideas I will be pronouncing and verbalizing, just in case if you are not in the mood to cut paste all things. Second spin sigma 2 T2 alpha enter B. Then multi-spin system. Multi-spin system. Well, we are not claiming that it will be a product of those. We are just developing the feeling of how big the basis is. You know that we are going to arrive to conclusion that instead of product there will be Slater determinant. So for multi-spin system, it is just only basis. Only basis. Sigma 1 times sigma 2. So we just multiply these two. see. And if we open the brackets, we do see that the basis will contain 4 independent functions. So first spin in state alpha, and second spin in state alpha, and first spin in state alpha, second spin in state beta, then first spin in state beta, second in alpha, and then both first and second are in state beta. So our quantum states of 2 spins are determined in basis of 4 possible basis functions, which enlist all possible chances. But there is a possibility that it is not one of those, but superposition. You may want to put specific coefficients for each of those basis states. C alpha, C beta, C beta alpha, C beta beta. Okay. So those 4 basis states, meaning that system of 2 spins probably can exist at least can exist at least in 4 different states, and the natural states that do appear for this system should be eigenstates of Hamiltonian, right? And in spin systems, a little bit of adjustment in this requirement. The eigenstates of this system should be simultaneously eigenstates of total spin squared and z projection of the total spin. I want to avoid writing all those calculations. So I states total spin squared with z projection. So what one is trying to do is to do this total spin squared acting on this sigma 1, sigma 2, getting some quantum number, then obtaining back the same quantum state. And the solution of this eigenstate equation will give the values of this quantum number and will give the specific realizations of the spin state. And realizations of the spin state will be specified by specific values of those C alpha alpha, C alpha beta coefficients. Values for beta coefficient. So there will be 4 sets of these 4 numbers, so total 16 numbers, 4 solutions, each solution represented by 4 numbers. And those 4 first, second, third. So one of them is when both alpha equals 1 and the rest equals 0. Alpha beta equals 0 equals C beta alpha equals C beta beta, which means that both spins are down. Then second solution is when C beta beta equals 1, which and the rest C alpha alpha, C alpha beta, C beta beta equals 0. So this corresponds to the situation that when both spins are up. And there is an opportunity when one spin up and one spin down. But when one finds the solution of those eigenstate equation, they're not coming as one spin up, one spin down. They're coming in a superpositional state. Alpha alpha equals 0, C beta beta equals 0, and C alpha beta equals plus square root of 2. Beta alpha equals also plus square root. And another solution is C alpha alpha equals 0, 0 C beta beta 0, and C alpha beta equals plus 1 square root of 2, and C beta alpha equals minus square root of 2. So those are a little more difficult to draw, but the number 3 is superposition of the one spin up, one spin down plus first spin down, second spin up. And the last opportunity is up and down minus down up. The energy of the spin configuration when it is when they are superimposed in this situation is the lowest, and in most cases it is what is coming up as a spin configuration in this multi-spin system, and this is prompting the simplest Slater determinant. Slater determinant, which we were defining as function 1, function f for object 1, function g for object 2, minus f for object 2, g for object 1. So electronic even spin system in lowest available state take this an antisymmetric shape. And then it follows it satisfies the Pauli exclusion principle. And based on analysis like this, the concept of Slater determinant was developed. Okay, so we completed briefly these subjects, and when we meet next time in person or through electronic means, we do need to develop mathematical tools that help to treat the Hartree-Fock theory, and specifically we will need to develop matrix elements of Coulomb interaction, because the idea of Hartree-Fock that we were discussing at the beginning of the lecture is that ions plus old electrons plus electrons that were already there interact with the new coming electron. And there, the Hamiltonian will explicitly include the contributions from this new electron interacting with the previous one. So one needs to determine matrix elements of Coulomb interaction. And what is very counterintuitive, there should be also some orbital indices. I just do not want to mislead you. There is a important counterintuitive thing. So the evaluation of Coulomb matrix element, when on the left and right part we do have the same orbital, same argument, here also same orbital, is intuitive. It just corresponds to electron density of first electron density of second electron, and they, especially if they are on some distances, there is a then when we integrate them, we get contribution to the energy. But what is happening in careful treating the Hartree-Fock theory, that sometimes those arguments and functions are swapping. And those swapped functions bring some constructions that do not have common sense analog. They do not have classical Newtonian mechanics analog. There are some specific quantum effects that need just careful mathematical accounting. But if one doesn't have them in the account, then theory gives very unreasonable results. So we are going to focus on the way how to treat electron-electron interaction, including some counterintuitive terms. Okay, I think it would be enough for today. So let me announce it as an end of lecture 11. But I will happily stay here and answer any questions if you have some. Yes, please. And I will try to match if several people want the same topic or no one wants to give some topic. I will try to find best match of the situation, so the distribution of volunteers between them. Okay, if there are no questions, then class is dismissed.
Can I ask about last lab maybe? Can you briefly tell us what we have to do, what you did on last lab, and we'll try to do, and if we got problem, we can ask. What you basically did